Yes. If we consider a closed system is I need to pin this thing down so it will not be giving problem. So this computer is misbehaving today. I don't know why. So what is the problem? Okay, yes. So now let's proceed. So for a closed system, we have something like this, a rigid vessel. So rigid vessel. Okay, so rigid vessel means that what are the characteristics of a closed system? So energy can enter. So energy is not equal to 0, but mass equals to 0. It means mass is not allowed to go in and out of the system. You understand me? So this is a rigid vessel. Another example of a closed system is a piston cylinder arrangement. So this is piston cylinder, okay, arrangement. And same thing over here. Here, as far as energy is concerned, energy is not equal to 0. Okay, so energy can go in and out of the system. Energy can go in and out of the system, as we have over here. We have E is not equal to 0, but mass is always kept constant. So M is always equal to 0. Okay, so these are the two classical types of closed systems or thermodynamics system that we have considered. You can also give another example, such as maybe open system. So in open system, you can give an example where we have, let's say, either a turbine like this. Okay, so we have inlet to the turbine. We have, or let's say a nozzle. I think a nozzle is better. Okay, so this is a nozzle, and this is the boundary of the nozzle. Okay, so this allows fluid to flow in and out. So it means mass can enter, heat energy can also enter. Okay, for the open system. So here, mass is not equal to 0. Similarly, energy is also not equal to 0. Okay, so energy is also not equal to 0. So it means energy can flow in and out. If it's not insulated, we can have Q in or Q out of the system. And here mass is going in, mass is coming out of the system. So this is also a thermodynamic system. Okay, I will not waste my time on this. Quickly, I'll move on to a very important one, which is the piston cylinder question. Okay, let us discuss that. Okay, according to this particular question, we are told that, the next question says describe the formation of acid rain. So what are the formation of acid rain in terms of its source and its impact on the environment? So here I'll not waste my time on it. You can refer to your lecture notes. So basically, what are the causes of acid rain? One of the basic causes of acid rain is that, you see, during the formation of ozone depleting substances such as carbon dioxide, SO2, okay, so formation of ozone. So now I'm considering this particular question, the B part. So this question. So there are certain substances such as carbon dioxide, SO2, NOx, NO2, or whatever it is. So when this thing is emitted into the atmosphere, okay, into the atmosphere, okay, by means of combustion or by means of, let's say, power plant cycles, okay, or even automotives, okay, so we can have automotive emissions from automotives, okay, they release these substances into the atmosphere. Now, this is trapped, these substances are trapped, okay, trapped in the atmosphere. And during raining, when it starts raining, immediately part of these substances, such as carbon dioxide and CO2 or NO2, NOx, they react with the water. So water plus, let's say, carbon dioxide. Okay, this eventually, it forms an acid. Acid is formed. Okay, so the chemical formula is not necessary over here. We are not chemical engineers. So there is acid formation. It's also, whenever you have, let's say, SO2, SO2 also reacts plus water. It also gives you acid. You understand me? So this acid, eventually, it is washed down into the soil. So the moment the acid gets into the soil, eventually it will form something like acid rain. And this is poisonous for human consumption. It will also go into the lake and so on, like this. So you can look into your lecture notes for the details about this particular chapter. Okay, now I will move on to the next question. So in the next question we have, okay, yes, so let's see. In this question, we are told that an insulated piston cylinder device contains, so this question is similar to the assignment which I gave you. Okay, so the cylinder contains 1.5 liters of saturated liquid. So 1.5 liters of saturated liquid, and then saturated liquid refrigerant 134A at constant pressure. So let us draw the diagram for this particular device. Okay, we have the piston is like this. This is the piston cylinder. Okay, and let's say we are told that the refrigerant occupies 1.4 liters and at constant pressure. So the pressure in the system is given by 120 kilopascal, as shown in the figure. So a paddle wheel. So paddle wheel means something like a paddle wheel like this, a shaft, okay, and provides or is used to stir the fluid. So the fluid is being stirred while a current of 12 amperes flow for 12 minutes through a resistance. So here we have the shaft work, okay, W shaft is this, and then there is current also, which means there is electricity. Current flows through, okay, so maybe this is the positive side, this is the negative side. So we have the current. So here we're going to have W electrical. W electrical. Okay, so the W electrical is the amount of electrical energy that enters the system in this way. So then this is piston cylinder arrangement. Okay. Now, if you look carefully, here we are told the system is operated at constant pressure. So it means that if we are adding heat, electrical energy to the system, and then we are adding paddle wheel work done also on the fluid. Okay, so since it's a constant pressure, the piston need to what? Expand, so that the pressure will remain constant. Otherwise, then there is no way we can maintain a constant pressure if the piston does not move. So then we assume that this is what we call a frictionless piston cylinder arrangement. Okay, so the piston moves. So it means that there is boundary work also associated with this movement. So this is called WB. This is the boundary work. So there are three types of work associated with this cylinder. This is similar to the assignment. One of the work is boundary work because of what? The movement of the piston. And another work, this is shaft work. This is not boundary work, this is shaft work. And then we have the next one is the electrical work. Okay, so these are the three types of work associated with it. Now, we are told that again, if 3/4 of the refrigerant is evaporated during this constant pressure process, and then the paddle wheel does 240 kilojoules of work. Determine the voltage of the source. Okay, so the whole thing is like this. Let's see. So let me make it a bit small. I think I should copy this thing again. Only this I'm interested in. I think it's better this way. Okay. So we have enough space like this. So clearly it is this way. We have the piston. So we have, let's say, paddle wheel. Is this inside the piston. And then we have the electrical resistance given by this. Okay. This is W electrical. So this is W shaft. And then we have W electrical. This is given by this. Then we have the boundary work. Because the piston is moving, so you have WB, which is the boundary work. Now, initial condition is that at state 1, or the properties is such that V1 equals to 1.5 liters. Okay, so this gives us about, in meter cube, about 0.0015 meter cube. Okay, then also the pressure in the system is given by P equals to, or P1 equals to 120 kilopascal. Okay, so the current that flows in the system is 12 amperes at 25 minutes. So the current flows for 25 minutes. Okay, so this 25 minutes means that delta T, the time, equals to 25 minutes. And 25 minutes in seconds, so that gives us 25 minutes times, let's see over here, 60 seconds divided by 1 minute. Okay, so this gives us 1,500 seconds. Okay, so that's the time. And again, the work done by the shaft work, W shaft equals to 240 kilojoules. All right. Next, we are also told, now we want to determine the voltage of the source. The voltage of the source. Okay. Also show the process on PV diagram. So we want to determine V. And we know by definition, W electrical equals to V times I times what? Times time. Okay. So, and the unit is in kilojoules. Okay, so it means we know the value for WE, we know the current, we know the time. So, important thing is that we can determine the voltage from here, but again, we have to make sure that, we don't know WE. WE is not given. I'm very sorry for that. WE is not known. Okay, if we know WE, then we'll think would have been. Okay, so but here our voltage is going to give us WE divided by current times delta T. Okay, so how do we determine the WE? So here it means we need to apply the first law of thermodynamics. Okay, let us sketch the whole thing again. The whole thing is like this. At state 1, we have shaft work. Let's say this is the shaft work at state 1. And then we have the electrical work. Okay, W electrical. So W electrical is this. And then we have W shaft. And then we have the boundary work. So this is the boundary work. So WB is the boundary work. Okay, so now at state 2, the same information, only that the volume is going to increase. So initial state is V1, volume V1, okay, is given already. So now at state 2, since it's a constant pressure process, the volume is going to what? Increase. There will be increase in the volume. Again, this is the shaft, And then we have our electrical. Okay, so the current, W electrical, and W shaft. So then the volume is going to increase over here. So there would have been some W work output, but boundary work. So applying the first law of thermodynamics, from the first law of thermodynamics, we know that from first law, also the question I gave you, the assignment, you have to apply the first law of thermodynamics. Okay, so we will have the total amount of energy entering a thermodynamic system minus the total amount of energy exiting should be equal to the change in energy of the system. Now, this quantity is always equal to 0. Okay? Oh, I'm very sorry. I'm very sorry for this. So, this is not like that. This is not like that. So, we'll have, it is only 0 for a closed system. I'm very sorry. Sorry, open system. So, we have, this is delta E, energy, change in energy of the system. Okay? So, this change in energy of the system is the same as delta U plus delta KE plus delta PE. Okay, potential energy of the system. So the total amount of energy entering the system can be in the form of mass, it can be in the form of work, it can be in the form of heat transfer. So we will have Q in plus W in plus what? Mass in minus the outlet, Q out plus W out plus what? Mass out. Okay, this should be equal to change in delta U plus change in delta KE plus change in what? Delta PE. So one of the basic assumptions to apply over here is that change in potential and kinetic energy are equal to 0. And if you look into the question again, you will discover that we are told an insulated piston cylinder. So insulated piston cylinder implies what? Okay, insulated piston cylinder. So this implies adiabatic. If it's adiabatic, then it means the net heat should be equal to 0. Okay, so it means Q in equals to Q out equals to 0. Okay, so there is no heat input. So Q in and Q out are equal to 0. Also, this is a closed system. So mass cannot go in, mass cannot go out. Only for open system that we have mass going in and out of the system. So now you see, we are left with what? W in minus W out. See, W in minus W out equals to what? Change in internal energy of the system. So now we have to classify what are the W ins in the system, what are the W out. As far as the cylinder is concerned, again, let me sketch over here. Okay. We have electrical, and then we have boundary work. Boundary work is this, W boundary. So W shaft, and then we have W electrical. So W in corresponds to W electrical because this is coming into the system. You understand me? And then we have W shaft also. So W in is given, there are two types of W in. We have W shaft plus what? W electrical. And what is the W out over here? So W out will correspond to boundary work. Okay, so if you organize this into the equation, so we will have W electrical plus W shaft minus boundary work. This should be equal to delta U. Okay, now we don't know the value for WE. So that's what we need to determine. Shaft work we know already. Boundary work, what is the equation for the boundary work? So boundary work is defined as PdV, and this equals to P into bracket V2 minus V1. Okay, so now if I put into the equation, I'll have WE equals to, and WE plus, so WE plus shaft should be equal to delta U plus WB. So delta U is the same as U2 minus U1, and WB is equal to, so plus, I'll have PV V2 minus V1. Okay, so we will establish a relationship between the internal energy and then the boundary work. So I'll combine U2 plus PV2 like this. Okay, so I multiply this by that and then add to this. So that gives me 1 bracket minus into bracket again U1 plus PV1. Okay, so what is the definition for these two? U plus PV, that is the enthalpy. So H2 minus H1. Okay, absolute enthalpy. H2 minus H1. So that's the whole thing. If you don't know this, then there is no way you can solve this question. So I'll express this in terms of absolute quantities. You can have M H2 minus H1 specific values. So that is our WE plus the shaft work. Okay. So now our aim over here now is to determine H1 and H2. So let us go back to the question and try to determine the state properties. So at state one, what do we know as state one? We are told the fluid is saturated liquid. So saturated liquid. Okay. And then the pressure, initial pressure P1 equals to 120 kilopascal. So eventually H1. So this is saturated liquid, it implies H1 equals to HF at 120 kPa. Okay, so can somebody tell me what is the value for this? And then specific volume V1 equals to VF at 120 kilopascal. Can somebody tell us what is the value for H1 and V1? At 120 kilopascal, let's see, 120 kilopascal, you go to saturated, Be careful, it is refrigerant, not water. Okay, the working fluid is refrigerant. So refrigerant can be found in page 19. Page 19. So now we look for pressure. Yes, saturated pressure. Okay, pressure table. So 120 degrees, kilopascal. HF corresponds to, so the HF corresponds to what? Let's see. From my table, I got 22.49. Okay, so 22.49. Can somebody cross-check for me? Ima, are you there?
Yes, sir. Right, 22.49.
22.49. Okay, so kilojoules per kilogram. And then specific volume for this gives me, that is VF. Oh yes, VF 0.0030. And then 7324.
Yes,
All
sir.
right, so now this is the situation. Okay, so now we need to, we don't know the mass of the fluid. Okay, so because we need to determine the value for M. How do we find M? We know by definition that specific volume, or let's say, specific volume V1 equals to absolute volume V1 divided by mass. So mass equals to the V1. V1 is given already. Okay, so we are told V1 equals to 1.5 liters. So that gives me 0.0015 meter cube divided by the specific volume. Okay, so then I will have 0.007324. Okay, so yes, so this is meter cube per kg. So meter cube per kilogram. So if you calculate this carefully, Ima, can you tell what is the result for that? Anybody with calculator? So I don't have my calculator.
2.048.
Huh?
2,
0.048.
no, sir, 2.048.
What?
2.048.
Oh, 2.0. Okay, thank you. Thank you very much. Okay, so kilogram. So that's the mass of the fluid. Now we know the enthalpy also at state 1. Now we need to move on to state what? State 2. Okay, so at state 2, what is the situation over there? Now, at state 2, so P1 equals to P2 equals to 120 kilopascal. So why do we have P1 equals to P2? Because we are told in the question. Let's see again. So where is the question? Yes. So this is the question. Sorry. Yes, in the question we are told that an insulated piston cylinder device contains 1.5 liters of saturated liquid at constant pressure, you see, of 120 kilopascal, as shown in the figure below. So a paddle wheel is stirs the refrigerant while a current of 12 ampere flows for 25 minutes through a resistant place in the refrigerant. If 3/4 of the refrigerant is evaporated during this constant pressure process. Okay, so it means that at the final state, at the final state, we have like this. Let me explain that for you. Initially, let me change the color. Initially, we have, let's say in this gadget, we have all is liquid. So this is liquid, saturated liquid. So initial state, this is saturated liquid. Okay. And then when the electricity is switched on, then the water starts what? Evaporating. So as the water starts evaporating, so then we will start having vapor formation over here. Okay, so the vapor continues until eventually at state 2. At state 2, we have some amount of liquid present in the system, and then we have some amount of vapor as well. This is the vapor. Okay, so but we are told that at the final state, the amount of vapor is 3/4 of the initial. So it means that, what does this tell you? It means that is the vapor fraction. So assuming you started with 100% over here, 100%. And by the time you move to state 2, part of this 100% is converted into vapor. And that percentage which is converted into vapor is 3/4. 3/4 means 75%. So it means at the final state, we will have 25% over here, and this is 75% of the vapor. Okay, so 75% of the vapor. 75%. And this constitutes 3/4 of the vapor. Okay, so whereas if this is 3/4, then this is going to be 1/4. So here, what they want to tell you is that the value for x, which is the vapor fraction, x equals to 3 divided by 4, which is what? 0.75. That's the value for x. Okay, so it's very, very, very important that we should notice this. So at the final state, so yes, so this is state 2. At final state, okay, value for x equals to 3/4, which equals to 0.75. So it means if I want to find H2 will be equal to what? HF plus X HFG. You understand? So that is going to be the H2. So now quickly we will determine from the property table, we will discover that let's say HFG equals to, again at 120 kilopascal. What is HFG? Let's see. HFG 120. How much?
214.48.
214.48. Thank you. Kilojoules per kilogram. All right. So then HF, what about HF?
22.49.
22. So 22.49. So kilojoules per kilogram. So it means H2, if you substitute into the equation, 22.49 plus 0.75 times 214.48. So eventually, this gives 183.35 kilojoules per kilogram. So that is H2. So now from this equation, we can determine W, our W electrical equals to mass of the fluid, H2 minus H1 minus W shaft. Okay, so now this gives us, what was the mass we got? The mass of the fluid, 2.048. 2.048. So this gives me 2.048 times 183.35 minus H1, 22.49. Okay, minus 240 is the shaft work. So this gives what? 89.44 kilojoules. Okay, so by definition, W electrical should be equal to VI times delta T. But be careful, we need to divide this by 1,000 in order to convert this into, because this, the whole of this, yes, so I think I should explain over here. So the whole of this equation, the unit is going to give us, unit for voltage is V, and unit for current is ampere, and unit for time is seconds. So this is called VAS. You understand me? So but I think, yes, 1 kilowatt or 1 VAS, VAS, equal to 1 kilojoules. Yes, 1 kilojoules. Okay. Let me see over here. Let me see, VAS equals to 1 kilojoules. And then let me see. So wait a minute. So this gives us one VAS, that is 1 VAS equals to 1 kilojoules. And then let me see, 1,000. Oh, sorry, it should be 1,000 instead. It should be 1,000. So this should be 1,000. Yes, so it should be 1,000 kilojoules. Okay, so this implies that this implies that 1 kilojoules will give us 1 VAS divided by 1,000. Divided by 1,000. So I divide both sides by 1,000. You divide this by 1,000. You divide this also by 1,000. So then this will cancel that. So 1 kilojoules equals to 1 VAS divided by 1,000. So that if you have this VAS and you want to convert it into kilojoules, then you need to divide by 1,000. You understand me? So then that gives us, we will have, let me see over here. Let me see. So we have to divide this by 1,000 in order to do the conversion for us. Okay, so let me check something over here. first before we proceed. Okay. Yes, so let me see. I think there was a mistake over here. Instead, it is supposed to be like this. It's supposed to be the other way around. Okay, so it's supposed to be like this. 1000 watts, sorry, 1000 VAS should be equal to 1 kilojoules. Yes, this is correct. So that 1 VAS is equivalent to 1 kilojoules divided by 1000. You understand me? So let me delete this part. Okay. So it means now the unit for this, as we see here, is given by VAS. V for voltage, A for current, and then S for time. Okay. So but we want to convert it into kilojoules. So how do we convert into kilojoules? We know 1 VAS equals to 1 kilojoules divided by 1000. So wherever I see this, I'll just replace by that. So then I'll have WE equals to nothing, VI delta T divided by 1000. So now this is now in kilojoules. The reason why we are doing this is that the shaft work is in kilojoules, and the heat transfer also should be in kilojoules. Okay. So now, if you do the substitution carefully, we will have we are interested in determining the voltage. So the voltage now becomes equals to, and the electrical work transfer, okay, so which we, let me see, which gives us, we have already calculated to be 89.44, okay, kilojoules times the current, okay, oh sorry, times 1000 divided by the current and then the time. So the current is 12 amperes times the time. Time is 1500 seconds. So if you calculate this carefully, this gives you 4.968 volts. Okay, so that's the voltage as far as this question is concerned. And then the last part, we are told to sketch the PV diagram with respect to the saturation lines. So the PV diagrams looks like this. Okay. Initial state of the fluid is saturated liquid. So this is state 1. And the final state is saturated liquid vapor mixture. And it is supposed to be here. This is state 2. And because this is a constant pressure process. So that's the solution to this particular question. Okay. So is there any question so far? Okay. And this is the solution to that question. Now, let us see if there is any other question we can look at, okay, before maybe we leave. finally. So is there any questions so far from any of you? Okay. And let me upload this other question. Let me upload this one. So I have one other question. So your test will only focus on chapter 1, 2, up to 3. And chapter 3 only up to first law of thermodynamics for closed systems. Okay? First law of thermodynamics of closed systems. So let's look at July 2019. July 2019. Let me see the question. So for this question, I'll just give you a briefing on it, and then you can try yourself at home. Okay. And that is there. So unfortunately, I cannot copy there. So yes. So this is the question. And we are told that consider a piston cylinder device. Okay. We have a piston cylinder device in which it contains carbon dioxide. Okay. And then with a set of stops. So we have 2 stops over here. Okay, as illustrated in the figure below. It's filled with carbon dioxide. So straightforward, you should realize that this is what? Ideal gas. Ideal gas. So ideal gas means you are allowed to use ideal gas equation. You understand? So initially the pressure, temperature, and the volume of the cylinder of the carbon dioxide is given to be, so P1 equals to 128 kilopascal, T1 equals to 135 degrees Celsius plus 273. Okay, so that need to be calculated. And then V1 also giving 0.038 meter cube respectively. The piston cylinder then undergoes a polytropic expansion. So it means it starts moving all the way. Okay, so this is the only boundary work we have. This is the only form of W that we have. We are told, look again, the piston undergoes the polytropic expansion until the piston head reaches the set of stops. So until the piston was here, sorry, yes, the piston. It was moving and then it knocked this surface. You understand me? So initially it starts from state 1 and then it moves, okay, up to state 2. And then it stops over there. It can no longer move. So it means that between state 1 and state 2, the process is called polytropic process. Polytropic process. Now, at this position, the pressure and temperature of the carbon dioxide. So it means at state 2, so it means P2 pressure equals to 87 kilopascal. Okay. And then temperature T2 equals to 68 degrees Celsius. Okay. And be careful over here. Don't be tempted to say that since the piston is moving from state 1 to state 2, it is never a constant pressure process. You understand me? So polytropic process is different from a constant pressure process. If it were to be a constant pressure process, constant pressure, then P1 will be equal to P2, but it's not a constant pressure. So it is a polytropic process. And for this polytropic process, it is initiated through in which the pressure changes. You understand me? So that's why we are told that P2 equals to 87 kilopascal, T2 equals to 68 degrees Celsius. You understand me? Okay? So it is not isothermal as also. Okay? And then the heat is then added to the carbon dioxide until the temperature reaches 103 degrees Celsius. So now let's see again. Start from state 1. It goes to state 2. Okay? At state 2, then heat again is added to the system. So it will move to a new location called state 3. You understand me? So here there is Q in added to the system in between these two states. This is polytropic process, and this is a different situation. Okay? Now, can you guess what is the process between state 1, so 2 and 3? Because if you look over here, the piston, when it reaches here, it can no longer go. So it means that between process 2 and process 3, this is called a constant what? Constant what? Can you guess? Between process 2 and process 3,
Pressure,
there is something which is constant what? There is something constant. You see, between state 1 and state 2, what is happening to the volume? Volume is increasing. Then it hits this, then it stops. It can no longer go. Now, at this state, more heat is added, Q in. So the moment you give more heat to it, the piston will try to push up, but it can no longer go. You understand me? So it is a constant volume. Between state 2 and state 3, this is a constant volume process. You understand? It's a constant volume process. Okay? Now, the piston cylinder is then compressed adiabatically. So now, when it reaches state, this particular final state, it is now compressed adiabatically. Okay, so adiabatic means that, what do you call it? There is no heat transfer in and out of the system. Okay, so at this particular state, the fluid goes back to its original state through adiabatic. So let's say if you want to draw the diagram for this process, the PV diagram is going to be like this. PV diagram for the whole cycle is going to be this. Initially, we have a polytropic process. So something like this. Okay? So the piston expands all the way from state 1 up to state 2. This is the expansion. And then from 2 to 3 is constant volume. Volume now will not change. This is constant volume. Constant what? Volume. And then, so this is state 1, state 2, state 3. Okay. So now, finally, we have the fluid. Let's see over here. So from 1 to 2, this is polytropic. And then 2 to 3, constant volume. Yes, this is it. And then, let's see. Oh, we have not finished. So adiabatically, so adiabatic means from state, the piston cylinder is then compressed adiabatically to a pressure of 112. Oh, yes. So we have not even reached the end. So let me delete this portion. Okay, so the piston tries to move to its, okay, state 4. This is adiabatic. So this is adiabatic. Okay, so adiabatic means we have a situation like this. Okay, so I'm not drawing it properly. So this adiabatic. Okay, adiabatic situation is this. So this is adiabatic. And then finally, the piston moves back to the initial state isothermally. Yes. So this is the isothermal. Isothermal. This is the isothermal line. So this is adiabatic, this is isothermal. Okay. So now the word isothermal means PV equals to a constant. Okay, so isothermal means PV equals to a constant. And then similarly, let's say if we, for between state 3 and state 4, okay, so that is our adiabatic process, and that is, there is no heat transfer to the whole system. Then we are going to have a situation where we have PV raised to the power K equals to a constant. Okay. And then for this polytropic, PV raised to the power N equals to a constant. So we should know all these things. Very, very, very important, very necessary. Okay. So now, determine the network for the compression process by taking specific heat at room temperature. So we want to determine the network for these processes. What do we mean by network? So when we say network, it means, so the network W net is simply given by W, the total work done from state 1 to 2, plus 2 to 3, plus what? W3, yes, so this is state 4 to 4, and then we have plus W and 4 to 1. Okay, W4 to 1. Now we need to determine the work done. So W1 to 2. What is this? W1 to 2 is a polytropic process. Okay, polytropic. So for all polytropic process, that gives us P1 or P2 V2 minus P1 V1 raised divided by 1 minus N. N is the polytropic index. You understand me? N is called a polytropic index. So in the question, if we know P1, P2, and then V1, V2, we can easily determine the value for N. N is an unknown parameter here. Okay, so we have to find N. So how do we determine N? We can use this equation. P1, V1 raised to the power N, P2, V2 raised to the power N. So N will be equal to log of the pressure, that is 128 divided by 87, okay, all divided by, and let me see over here. Oh, sorry, we need to determine the volume. So the volume is not known, V2 is not known. Okay, so we need to determine V2. Okay, so let me delete the whole of this. Yes, so basically here we will have P2 divided by P1 equals 2. Then I divide this by P1. So then that gives me, this is V1. So that gives me V1 divided by V2 raised to the power what? N. Okay. So that if you take the log on both sides, we'll have log of, so N equals to log of, you take log on both sides, so then you have log of P2 divided by P1 divided by log of V1 divided by V2. Okay, so now let's see, according to the question, do we know all this? What are the known parameters? You see, P1 is known, V1 is known, also P2 is known. Okay, so T2 is known, but we don't know V2. So how do we determine V2? We have to use the ideal gas equation. Okay, so find V2. So we, from ideal gas equation, P2 V2 equals to MR T2. Okay, so V2 now gives me M R for carbon dioxide. Okay. And then times the temperature T2 divided by P2. So mass also is not known. So we need to determine the mass. So we have to use, since we know pressure, temperature, and then volume at state 1, we can use this P1 V1 equals to MR T1. So mass gives me P1 V1, okay, divided by T1 times R, the ideal gas. This gives me, if you calculate correctly, 0.0631 kilogram. So now our V2 gives me M 0.063 kilogram. Ideal gas, what do you call it? Constant for carbon dioxide. Okay, so it should be in the property table. Okay, so ideal gas constant for carbon dioxide, it should be in the property table. Let's see, we have oxygen here, carbon dioxide, carbon monoxide, yes, carbon dioxide is here. So let's see, ideal gas constant for carbon dioxide. Okay.
Zero point 1889.
Oh, thank you, thank you. How much?
0.1889.
1889. Okay, so kilojoules per kilogram per Kelvin. And then multiply by the temperature. Temperature, T, T2. So we have to add, T2 is how much? 87, right? Let me see. T2, yes, 68. 68 plus 273. 68 plus 273. So this will be in Kelvin, all divided by, so the pressure. So pressure, the P2 also gives us, we are told P2 is 87. P2 is 87, okay, kilopascal. So if you calculate this carefully, and the V2 should give you 0.6467, okay, 2 meter cube. Okay, so maybe somebody can help me calculate. Okay, so anyway, so let's move ahead. So important thing now is to determine the value for N. N equals to, this gives us log of P2 divided by P1. So means, let me see, 87. Yes, P2 is 87 divided by, let me see, so P1 is 128. Okay, 128. 128. So that gives us log of P2, 120, sorry, 87. 87 over 128. Okay, all divided by log of the volume. So log of, so we have log of the volume. So the volume is, this gives us V1 divided by V2. So V1 is 0.3, 0.038, 0.038, 0.038. Yes, so we have 0.038 divided by, yes, so V2, 0.64672. Okay, so let's see, 0. I'm at, can somebody cross check this for me?
point or cross check.
Hmm. Can somebody cross check for me? I think there is something wrong. It's supposed to be
0.0466.
thank you. 0.046.
66.
Thank you. Okay, so that is V2. So we have 0.0462. So we have here log of 87 divided by 128 divided by log of again 0.038 divided by 0.0466. So how much is this n? Can somebody calculate for me? Let's hurry up. It's almost 4 o'clock.
1.89.
1.89. Yes, so that's the correct answer. So now, you see, now we can calculate the boundary work. W12 equals to P2 V2 minus P1 V1 minus N. So if you calculate this carefully, you get about 0.9198 kilojoules. Okay, so now we need to attend to process 2 to 3. That is iso what? Isocoric, constant volume process. Okay, constant volume process. So for isocoric process, who can tell us immediately? You should know the boundary work W 23 okay equals to P V3 minus V2. This should be equal to what? If you look into the diagram, sorry. If you look into can you see the diagram? V2 and V3. What is the difference? Can you see the diagram, Ayman?
Constant, yes.
Yes, so V2 and V3 are what?
Same.
The same. So it means the boundary work for the constant volume is always equals to, this will give us 0. Because V2 and V1 are the same. Sorry, V2 and V3. So V3 is the same as V2. So the boundary work equals to 0. So we need to move on to the boundary work for process 3 to 4. Okay. So now 3 to 4 is adiabatic. Okay. So process 3 to 4 is adiabatic. Process 3 to 4 is adiabatic. Now, adiabatic compression. So now what happens is like this. In adiabatic compression, W boundary work 3 to 4 is given by P3 V3 minus P4 V4 divided by K minus 1. Okay, so now we need to determine the value for K as well. Okay, how do we determine the value for K? So we know that P3 V3 raised to the power K equals to P4 V4 raised to the power K. Okay, so just like we did for the value for N, similar case we'll do for the value for K. Okay, but here we don't know the value for P3. P3 is not given, so we need to calculate P3. Okay, so but we know that between state 2 and state 3, okay, so to determine P3, find P3. Okay, so we will consider process 2 to 3, where we have P2, V2, this equals to MR, T2, P3, V3 equals to MR, T3. So if I divide these two equations, this is constant volume process. So this and this will cancel, this and this will cancel out. So eventually, I'll be left with P2 over P3 equals to T2 over T3. Okay, so T3 we know already. P3 is what we are interested in. P2 also we know already. Okay, so if you calculate this carefully, P3 will give us 95.93 kilopascal. Okay, so then we can use this to calculate the value for N, because we know P3 V3 raised to the power K equals to P4 V4 raised to the power K. So if you substitute all the parameters, K will give you 1.289. Okay, so then let me see over here. The value for V4, let's see, we determine V4 already. Go back to the diagram. Okay. So we have told that finally the piston moves back to the initial state isothermally. Okay. And then the piston the piston cylinder is then compressed adiabatically to a pressure of 112 kilopascal. Okay, so it means P4 is 112. Yes, P4 is giving 112. And then let me see, V4 is not known. So we can determine V4 using this equation. Okay, so V4 can be determined. So we will establish a relationship between state 3 and then state 4 in order to get the value for. But again, let me see, before that, And the value for K, was not also given. Let me check in the question again. Checking the question, original question. Let's see. Okay, so the value for V4 is not given. Coming. So 1 minute, I'm checking something over here. So let me see. So I made a mistake somewhere. So I should have determined the value for V4. Okay, so then after I've got the value for P3, yes, so 1 minute. Okay, it seems to me that the value for K is already has to be given. The value for K should be given. Okay, so there is no need for us to calculate the value for K. K has to be given in this question. Otherwise, then we cannot solve this. Okay, yes, so the value for K should be given, which is from this particular value. And then from this, we can get the value for V4. Okay, so from this equation, V4 gives us 0.04143 meter cubed. Yes, so now we can determine the value for W. W34 equals to P3 V3 minus P4 V4 divided by 1 minus K. Sorry, K minus 1. K minus 1. So K minus 1. So if you calculate this, you get minus 0.5478 kilojoules. Okay, so now the last one, we need to calculate W41. This gives us, W41 is isothermal, and that is P4 V4 log of V1 divided by V2. And this, divided by V4. If you calculate this, minus 0.4 kilojoules. Okay, so now the total work done, or the net work done, is this plus 0 plus W 1, 2. Okay, so the net work, we are told W net equals to W 1, 2 plus W 23 plus W 34 plus W 41. Okay, W12, I think we have already done that. W12, 120. Yes, so 0.919. And then W223 is 0. So 0.1918. So we have W net 0.9198 plus this is the constant volume process, so it's 0 plus W23 that gives 34 that gives us minus 0.5478 and then minus again 0.4. So what is the final answer? Can somebody tell us what is the final answer? So this will be our last discussion. Yes, Ayman, 0.9198 plus 0 minus 0.5470 minus 0.4. How much?
0.028. Negative
0.028.
0.028.
Okay. So kilojoules. So this is the end of this tutorial. Okay, so if there is any question, let us discuss now. Okay, otherwise we will stop over here. Okay, is there any question so far? Okay, so if there's no question, thank you very much. We will have our test next time. And sorry for disturbing you also. Okay, so it's a holiday, but we don't have any choice but to, because we need to finish this particular topic.